Hello, I am Sam Smith, and this is Sam's Mcat Basics. This podcast covers the most important topics put out on the AAMC Mcat each year, and I determined this list by going through all the official practice materials that the AAMC puts out, and also some third-party practice material, and just put together this big list of topics that consistently kept on showing up, and ranked those topics and made podcasts. This lesson covers acids and bases, and it covers a pretty wide range of topics within acids and bases. So I'm going to cover the basic definitions of acids and bases, talk about calculating pH, then I'll cover titrations, then buffers, and lastly I'm going to talk about the blood buffer system that keeps your body in homeostasis, keeps your blood pH at about the same level. And acids and bases will be seen on 2 out of the 4 MCAT sections. They'll be seen on the chemical and physical foundations of biological systems, as well as on the biological and biochemical foundations of living systems. And I just want to note that some of this information is very, very basic, so this will bring you all the way back to freshman intro chem. But with that said, it's still very important. Make sure you know all these definitions, all these ideas, like the back of your hand. Make sure you really have all this stuff down. So very basic, but this will be a good review of all these basic topics. So the first thing I want to start with is some of the basic definitions of acids and bases. So the first definition was put out by Arrhenius, and he defined an acid as any species that increased the concentration of hydrogen ions in aqueous solution. And on the flip side of that is the Arrhenius base, which is any species that increases the concentration of hydroxide, which is OH minus, in aqueous solution. Then along came Bronsted, who was a chemical engineer, and his friend Lowry, who was a physical chemist, and they came up with the idea of a Bronsted-Lowry acid and base. And so a Bronsted-Lowry acid is a proton donor, or an H+ donor, and a Bronsted-Lowry base is a proton acceptor. It accepts protons. And so you can see this obviously in water. Water can either act as a Bronsted-Lowry acid or base. If it is accepting a proton, it can accept a proton and turn into hydronium, H3O+, and then it can donate that proton away. So when it accepts that hydrogen, it's a base. But when it's a hydronium ion and it's giving that hydrogen away to become H2O, water, it becomes a acid. And then the next definition, also the kind of most complex or kind of difficult to understand and difficult to see straight up, is the concept of a Lewis acid and a Lewis base. So a Lewis acid is defined as an electron pair acceptor, and a Lewis base is defined as an electron pair donor. So if you remember in organic chemistry, you can have pairs of electrons attack or pairs of electrons be basically accepted. You can have electrophiles and nucleophiles. A nucleophile is a reactant that provides a pair of electrons to form a new covalent bond, and a electrophile is the opposite. It is a species that accepts a pair of electrons to form a new covalent bond. And so if a pair of electrons attacks some atom, that would be a Lewis acid-base reaction. For the sake of an example, let's say you have ammonia, which is NH3, and it's got a lone pair of electrons, and it attacks boron trifluoride. And so these electrons that are the lone pair on the nitrogen of ammonia attack the boron, which is the electron acceptor. And so you could say the nitrogen, which is donating those electrons, is the Lewis base, and the boron, which is accepting those electrons, is the Lewis acid. And it's important here to note that that a Lewis acid-base reaction does not need to include the transfer of a proton. So that's something to look for. I'm sure I do this as well, but you think, okay, it asks me, is this an acid-base reaction? Well, there's no transfer of a hydrogen ion. Of course not. Well, that's not always the case. Remember to make sure that there's no transfer of an electron pair before answering the question no, because there might be. So one useful thing then is to understand how to recognize Lewis acids or bases just kind of by looking at them without tracking electrons. What in a compound should make you think, okay, this might be a Lewis acid? All right, so with Lewis acids, and remember these are electrophiles, there are two things that you should recognize that will make you think, okay, this might be a Lewis acid. And that's number one, a compound that has less than 8 valence electrons. So this is going to be something, and again, this is where the central atom has less than 8 valence electrons. So this is going to be something like boron trifluoride. And then the second thing you want to notice is a compound in which the central atom is capable of expanding their valence shell beyond 8. So this is something like phosphorus pentachloride, which is PCl5, or SF4, something with a bunch of bonds. You want to look at that and say, okay, that is expanded beyond its 8 valence. It's 8 valence electrons. That is possibly a Lewis acid. And then for Lewis bases, remember these are nucleophiles. And these are a lot easier. You just want to basically look for a lone pair of electrons, and that should tell you, okay, this thing is probably a Lewis base. And lastly, a Lewis acid-base reaction forms a Lewis adduct, which is just the product of a Lewis acid and base reaction. All right, moving on. Let's talk a little bit about the definitions of strong and weak acids. So what is a strong acid? So a strong acid is something that completely disassociates. And what I mean by disassociates, I mean that this acid dissolves in solution and that there's no more of the protonated form of this acid. Instead, you are left with just conjugate acid and conjugate base. So for example, HBr, which is hydrobromic acid, a strong acid completely dissociates, so then you have all hydrogen ions and all bromine ions as it disassociates. And so there are 6 of the strong acids to know for the Mcat. These are hydroiodic acid, which is Hi, hydrobromic acid, which is HBr, hydrochloric acid, which is HCl, perchloric acid, which is HClO4, sulfuric acid, which is H2SO4, and nitric acid, which is HNO3. And so you can remember that the first 3 at least, I, B, Br, and Cl, are all halogens on the periodic table, which is the furthest column to the right. So as I'll talk about a little bit later, the strong acids and bases are the easiest to do calculations for and are the easiest to figure out titration curves for, etc. That's really what you want to be working with. Of course, that's not always the case, but those make for easy calculations. And so moving on to a strong base, in the same way, a strong base completely ionizes to fully form its conjugate acid and leaves none of that base in solution. And so an example of this is a metal hydroxide. So let's take lithium hydroxide, which is LiOH. And so it fully disassociates into a lithium ion and a hydroxide ion, which makes it a strong base. And then, as you could probably guess, or as you probably know, the weak acids and bases do not fully ionize or dissociate in water. There's still some of that original acid or base left in solution at equilibrium. If time were to go to infinity and you let it just sit there forever, it's not all going to dissolve. It's going to sit with some of that acid still left. And so an example of this is acetic acid, which is the acid component of vinegar. And so only about 0.4% of the acetic acid that's in solution actually disassociates. So that makes it, 99.6% of acetic acid in solution is still in that protonated form. It doesn't give up its proton. And that's an example of a weak acid, a weak base, however less common, you still need to be familiar with. And one of these is ammonia. Ammonia in water in aqueous phase disassociates into NH4, which is called ammonium, and basically takes a proton from water, so it produces OH minus. And again, only a very small percent of these actually disassociate, and it's around like 1%, plus or minus 0.5% of these actually disassociate. So it's a very small fraction. So now that I've covered these basic definitions and concepts regarding acids and bases, let's get into calculations involving acids and bases. The most common problem you're going to see involving acids and bases on the Mcat is calculating pH. And so this should be a breath of relief for you. Calculating pH is super easy. However, it's a place where you can make you can make a mistake easily. And so I'm going to go over how not to make these mistakes. So when you're calculating the pH for a strong acid, it's very straightforward. You just need to use the concentration of reactants to calculate the hydroxide ion concentration after this reactant has fully disassociated. And then you use the equation, pH is equal to negative log of your H plus, and boom, you got pH. So when you're doing this, you need to take into account stoichiometry. Stoichiometry is where a lot of people have problems, including myself, so it's a place you really need to pay attention to when you're doing acid and base calculations. So say you have a 1 molar solution of sulfuric acid. So remember, sulfuric acid is H2SO4, and it really might ask you sulfuric, so make sure you know names and also how many hydrogen are with each strong acid. So 1 molar sulfuric acid, what is the pH of that solution? So you look at sulfuric acid, H2SO4. If it were to fully dissociate, you'd have 2 protons per 1 mole of H2SO4. So for each H2SO4, you have 2 protons when it dissolves. So you have a 1 molar solution. You're going to multiply that by 2 because you have 2 hydrogens, 2 hydrogen per mole of sulfuric acid, and that's 2 moles of hydrogen ions. So then you do negative log of 2, which is negative 0.3. That's not right. Boom, that is right, negative 0.3. So something also to remember, and this is a good example, is that pH can be negative. It's not physically impossible for it to be negative. It's not like in physics where you're calculating a distance and you get a negative distance, and you're like, shit, that can't be. You can have a negative pH, and as Tupac says, sometimes that's just the way it is. Let me briefly summarize what I just discussed. So for a strong acid, find how many hydrogen ions disassociate, multiply that by the concentration of your reactant, plug that into negative log of H plus, and you have the pH. And for POH, it would be the exact opposite process. Well, it would be the exact same process, but you do that with hydroxide ion or OH minus concentration. And don't forget that the lowercase p of anything is the log base 10 of that thing. So, you might see some notation on the Mcat where it says little p of, anything. For example, take density, p, little lowercase p, rho, which means density. That would just mean the negative log of density. And so after I talk about weak acids, I'm going to go through how to quickly do logarithms in your head. Another great skill to have on the Mcat. So calculating the pH for a weak acid is a bit more complicated. You need a disassociation constant, which is a Ka or Kb, depending on Ka is acid dissociation constant, Kb is base dissociation constant. And you're definitely less likely to see this on the MCAT, but I would still know it. And so if you think back to freshman chemistry or, even AP chemistry in high school, think back to ice table. And these are a quick way, you just draw it up on your little board you have for the MCAT when you're taking it. Drop a little ice table and solve it. And so, again, the I stands for initial, the C stands for change, and the E stands for equilibrium. And so if you remember, a disassociation constant is simply an equilibrium statement. So it's just the concentration of the products over the concentration of the reactants. And each of these concentrations is raised to the power of their stoichiometric coefficients. And it just simply says, if you were to leave this reaction sitting here for all of time at this infinite time point, the concentrations would be boom. And so, so concentration products over the reactants
raised to the power of their stoichiometric coefficient,
and that's equal to Ka or Kb. So that just tells you what those concentrations are. And so first thing you do, fill out your ice table. You have your initial. Usually you know the concentration of the reactant, and you do know the concentration of your products because they're zero. And that initially they're zero. And then you fill in the change, which is usually in X because it's unknown. And then you fill out the equilibrium part, which is where you say, okay, initial minus your change is equal to your equilibrium concentration. And then you take these equilibrium concentrations and you plug it in to your dissociation constant you plug it into your equilibrium expression, which is concentration of products over concentration of reactants. And then you go ahead, you solve for X, and then that's your change. You plug it back in and you find your end concentrations. Pretty easy, kind of. And from that, you can figure out, okay, this is how much protons disassociated, or you can find the proton concentration or the hydroxide concentration. And then again, you use negative log of your proton concentration, which is pH, or POH is your negative log of your OH concentration. And that is how you solve that.
All right, so let me just quickly summarize what I just went over. So when you're given a weak acid problem, you're most likely going to be given the concentration of this weak acid or weak base, and then also the Ka or Kb. And then what you want to do from there, draw an ice table, fill in what you know. What you don't know, label with X. Once you have that all filled out, you can plug in your knowns and unknowns into your equilibrium expression. This is all going to be in terms of some variable X. Then you're going to solve for that X. Once you have that X solved, you can then solve for the hydrogen ion concentration. And then the easy part, the pH is equal to the negative log of the H plus concentration, or the hydrogen ion concentration. Same goes for POH, negative log of the OH minus concentration.
And so it's good to know also how to convert between POH, pH, and your concentration of H pluses, concentration of OH minus. So this is pretty easy to remember. pH plus POH must equal 14. So sometimes it's going to ask you to calculate the POH of an acid. And so this is kind of a trick question, right? Because you're thinking, okay, pH of an acid, or you're thinking POH of an acid, but you're kind of in your head, you're thinking pH, you're thinking acidity, and you miss that. And so don't miss that. If your pOH is low, that means that you have something that's a base, and if your pOH is high, then you have something that's an acid. So it's the opposite of a pH. And then to convert between H plus and OH minus, you use Kw, which is the disassociation constant of water. And that is 1 times 10 to the minus 14. And so you have that your Kw is equal to your hydrogen ion concentration times your OH minus concentration. So keep in mind that this always holds. Your hydrogen ion concentration times your hydroxide ion concentration is always equal to 1 times 10 to the minus 14th. So you can convert between those as you wish. So I'm going to briefly touch on the quick and dirty logarithm calculation method that I used on the test, just, save time. So first, what is a logarithm? So a logarithm is the inverse function to an exponential. Basically, this means that the logarithm of some given number is the exponent to which another number, say 10 in this case, must be raised to produce that number. In other words, let's say you have log base 10 of, in parentheses, 5 is equal to x. What that's really saying is 10 to the x is equal to 5. What number is x in order that 10 raised to that power is 5? So essentially, what you can do is when you have a hydrogen ion concentration, put it in scientific notation right away, always. And once you have it in scientific notation, you're going to have, negative log to the 1 times 10 to the minus 4, for example. All you do is you take that exponent, multiply it by a negative 1. So log base 10 of 1 times 10 to the minus 4 is equal to 4. So if your hydrogen ion concentration is 1 times 10 to the minus 4, then your pH is 4. So just pick out the exponent each time. Negative log of 1 times 10 to the negative 5th, that's a pH equal to 5. Negative 6, pH equal to 6, and so on. Of course, this gets more complicated when the multiplier out front is not 1, and you can just use an estimation in this case. So let's say you have negative log of 3 times 10 to the minus 4. Well, the exponent is negative 4, and so that's the first thing that should come to mind, negative 4. However, the leading coefficient is 3, or the leading number is 3. So you know that this number has to be between 3 and 4. Because this is a negative log, you have to go down. So I think the tendency here is to say, okay, 3 times 10 to the negative 4 is a bigger number than 1 times 10 to the negative 4. However, that pH is actually lower. So the tendency here is to say, shouldn't it be between 4 and 5 because you have 3 times 10 to the minus 4? It should actually be smaller because of that negative leading part to the log. So the actual answer here is that the negative log of 3 times 10 to the minus 4 is 3.5. However, as you know, you don't have a calculator for the Mcat. So usually, and I say usually because I don't know exactly for sure, but every case I've seen, I'm able to just estimate this number and kind of pick it out. It's never, there's never question of, okay, there's two numbers it could be two numbers, which one is it? I know the answer is between 3 and 4, but there's 3.5 and 3.2, which one is it? Everything I've seen, you can just estimate it and say, okay, this number is between 3 and 4. I'll pick 3.5 because that's the only one that's between 3 and 4. So again, negative log, pick the exponent out if the multiplier is 1. If the multiplier is above 1, you go down. So you say, okay, the exponent is negative 6, and the multiplier is 5. Well, I know it must be between 5 and 6. All right, so the next thing I'm going to talk about are titration curves and buffers. So starting off with titrations, what is a titration? So a titration is a common laboratory method used in quantitative chemical analysis that basically is used to determine the concentration of some unidentified solution or unidentified analyte. And so basically, in other words, you have an acid, but you don't know its concentration. Is this acid harmless, or is this something that you could use to decompose a body, like in Breaking Bad? So then, how does this titration thing work? So essentially what you're doing is you have an acid and a base, or vice versa. It must be one or the other. And what I mean to say is you can't titrate an acid with an acid or a base with a base. And what you're doing is you are adding a amount of known concentration solution to a solution of unknown concentration, and then you're watching for an equivalence point, and from there you can figure out what your unknown concentration is. And so real quickly, I'm going to go over a few terms that you're likely to see when it comes to titrations. The first is titrand. So your titrand is your solution of unknown concentration. And the next term is a titrant, and that's your known concentration that you're adding in order to figure out what your unknown concentration is. And then you also have the equivalence point, as I mentioned. And so the equivalence point is the point in an acid-base titration in which the moles of base equals the moles of acid, and therefore the solution contains only salt and water. So what exactly does that mean? Say that you're adding sodium hydroxide or NaOH to hydrobromic acid, HBr. As soon as your moles of H or your moles of proton, where protons are equal to your moles of hydroxide in solution, you essentially only have water, because the protons in the hydroxide reactive form water. You only have water and salts, which are your bromide or Br minus, and then sodium, which is Na plus. And so to be able to see this equivalence point, you use what's called an indicator. And so an indicator changes colors as close to the equivalence point as possible. And it's important to know that a lot of these indicators aren't going to be exact. There's a range in which they change colors. So sometimes you're going to have an equivalence point that is below an indicator, below a color change, or above a color change. So it's not always perfect, but this is one of the better ways to do it. Other than you could track pH if you have a pH meter, but this is a better way to visually be able to see where the equivalence point is. So then an important question becomes, how do I choose an indicator? And I did see a few problems like this on the Mcat, so take special note that you might see something like this. So there's a bunch of different kinds of indicators. Just to name a few, we have methyl violet, bromophenol blue, methyl orange, methyl red, litmus, bromothymol blue, phenolphthalein, azurin yellow, and more. But choosing them is a bit complicated. And what you want to do is you want to pick the indicator with a pKa closest to the equivalence point. Again, a pKa is just the negative log of the Ka, which is the acid dissociation constant. And you can think of the pKa as the pH in which half of the indicator molecules are protonated, which would result in color 1, let's call it, and where half the indicator molecules are deprotonated, and we'll call that color 2. So basically, you need to be given a table in which you have the pKa or the Ka values of these indicators, and then you pick the one with the pKa closest to the equivalence point. And so for a strong base, strong acid titration, that's 7. If it is a strong acid being titrated with a weak base, that's a little bit below 7. And if it is a weak acid titrated with a strong base, it's going to be a little bit above 7. And so you can kind of remember that, pick the pKa closest to that equivalence point. Moving forward here, so you have your setup here. You have your titrand, which is your unknown solution, and you're adding a titrant to it, which is your known concentration. So what you do is you're slowly dropping in the titrant, and you are watching for a color change. So you have your indicator in with your unknown compound, and you're watching for that color change to occur. And so you're dropping it in, dropping it in, dropping it in. And of course, you record your initial volume that you start with of your titrant. And you're dropping it in, boom, you see a color change. You record the volume of titrant that you used. And then you use the famous equation M1V1 equals M2V2. And so that basically is saying that your moles of base are equal to your moles of acid. And so M1 in this case and V1 correspond to your acid, and M2, V2 correspond to your base, or, one corresponds to the titrant and the other to the titrand. And again, it is really important to remember to take into account stoichiometry. So
You might have an acid
like sulfuric acid that is strong, dissolves completely, but dissolves into 2 protons. And so to take that into account, you need to multiply your molarity by 2, because when you throw in a certain amount of sulfuric acid into solution, you're going to get twice as many protons, so it's going to take twice as much base. So remember to take that into account. Always multiply your molarity by the number of proton ions or hydroxide, depending on the stoichiometry. And do a few practice problems, you'll see it's pretty easy. And to further complicate things, there are titrations in which you can use strong acid and a strong base. Those are the easiest, but then again, you can use a weak acid and a weak base, or a strong acid and a weak base, or a strong, what's the last one? Oh, yeah, or a strong base, weak acid. And each one of these has its own kind of caveats, or has its own weird things that it's got going on. So I'm going to talk a little bit about that. So I'm going to start with the easiest case here, which is the strong acid, strong base titration. In this kind of titration, the most important thing to note is that your equivalence point is always going to be at 7. That's because the strong acids and strong bases fully disassociate, as I talked about earlier, and you're left with salt and water at the end of the titration. Now, in the next titration case, let's say that you are titrating a strong acid with a weak base. So that means that you have the strong acid of unknown concentration and you're dropping in some weak base. So in this case, your equivalence point is going to be lower than 7. And so I kind of like to think about this in a non-scientific way. You add in a strong acid versus a weak base, the strong acid is going to win, and you're going to have a pH that's lower than 7. And another important thing about the titration of a strong acid with a weak base is that your final pH is going to be lower than if you were using a strong base, which makes sense. A weaker base is going to be, for the same amount, is going to be a lower pH than if it were a strong base. And lastly, that brings us to the last case of a titration here that I'm going to talk about, which is the titration of a weak acid with a strong base. As you could imagine with what I've said before, the equivalence point is going to be, boom, above 7, because you are adding strong base into a weak acid. Strong base is going to win out. Your pH is going to be a little bit above 7, which is basic. And again, another important thing to say about the titration of a weak acid with a strong base is that your pH to begin with is going to be higher, since you have a weak acid sitting there that doesn't fully deprotonate, that gives off less of these protons into solution, so the pH is going to be a little bit higher for this weak acid in comparison to the strong acid. And one last thing to be said about any titration in which you have a weak acid, strong base, or a weak base, strong acid, is that you will see a buffer zone. And so the buffer zone is essentially this small little hump right at the very start of your adding of the titrant. So you'll see a slight increase and then it kind of flattens out. And so I'm going to talk about buffers next. But essentially what's going on here is, as you add more of your titrant, you're not seeing a big change in pH. The system is being buffered in terms of maintaining its same pH. And this buffer zone occurs right around where the pH equals the pKa. And as I said before, this is where half your acid is protonated and half your acid is deprotonated. Another term you might see to describe this point in which the pK equals the pH is called the half equivalence point. And before I move on to talking specifically about buffers, another term you should probably know is PI, which means isoelectric point. And this indicates the pH in which a protein has a net charge of 0. So this has to do with the deprotonation, protonation states of the amino acid residues. As the pH is raised, the protein tends to become more negative because more and more of these amino acids are deprotonated, leaving it negatively charged. And so you might see something that talks about a protein that has a low PI. What amino acids does it tend to be made of?
I'll give you a little bit of time to think about that.
The answer is that a protein with a lower PI is going to be more rich in acidic amino acid residues, and that's because these are going to be negatively charged until you get way, way, way down on the pH scale, until you get down to 2, and it will finally become protonated, and that negative charge becomes neutral. And once you get enough of these negative charges to become neutral, your protein likely will become neutral. All right, so now on to probably the most important acid-base concept for the MCAT, and that's buffers. And you're definitely bound to see at least 1 or 2 questions on the MCAT about this. And so buffers play a very important role physiologically. They maintain the pH in your blood and other physiological compartments. And some disease states can alter this pH in the blood, which have very negative health effects. So to start, a buffer is defined as a mixture of a weak acid and its conjugate base, or vice versa. And a buffer functions to resist changes in pH. So if you're adding more acid to a buffered solution, it's going to resist wanting to go down in pH. And if you're adding a base, it's going to resist wanting to go up in pH. It's going to hang out in a pretty specific window. And real quickly, don't forget that a buffer can also be a weak base with its conjugate acid. You don't really see that very much, but a specific example that comes to my mind is ammonia, NH3, and ammonium, NH4+, which is the conjugate acid to ammonia. Now, you might see a calculation on the MCAT, probably not. It's usually just more conceptual questions about buffers. However, you might, so I'm going to go over the famed Henderson-Hasselbalch equation that you might remember from Gen Chem in either your freshman college year or your high school years, whatever, or whenever you take Gen Chem. And it will give you, the Henderson-Hasselbalch will give you the pH of a buffered solution, and it looks like the following. In the case of a weak acid and its conjugate base pair, you have that the pH of the buffered solution is equal to the pKa of the weak acid plus the log of the concentration of conjugate base over the concentration of acid. And the basic form looks like the pOH is equal to pKb, which is for the weak base, which is the pKb for the weak base. And you add that to the concentration of conjugate acid over concentration of base. And of course, I can describe this equation all I want, and you still might not get it. So go ahead, do a few practice problems, make sure you are familiar with using the Henderson-Hasselbalch equation. And the number one application that is going to come up on the Mcat is the blood buffer system. You're really very likely to see this probably once on your actual test. And I'm not allowed to talk about the test that I took. Just know that I may or may not have seen that on my actual test. So to illustrate how the blood buffer system works, I'm going to give you guys an example of somebody working out and go through how exactly it works. So let's just say you just hit 10 sets of 200 pounds on bench. Your pecs are just popping, they're all pumped up, feels great. Your muscles are also using lots of energy. So as your muscles create ATP, one of the byproducts is carbon dioxide. And also lactic acid starts to build up because of this prolonged exercise. And it's pretty obvious with lactic acid, lactic acid is an acid. It would be able to decrease the pH of your blood. But carbon dioxide can combine with water and form carbonic acid, which again lowers your blood pH.
So these two factors together, the lactic acid and the dissolved carbon dioxide, lead to an increase in acidity of your blood, which is a decrease in pH.
So how does your body deal with this? Well, it uses the bicarbonate buffer system. And what the bicarbonate buffer system does is it produces the bicarbonate ion, which is the conjugate base to carbonic acid. And again, carbonic acid is produced when CO2 dissolves. And if you were to go the other way, let's say your blood is too basic, your body can also produce
carbonic acid to lower your pH back down to normal levels.
So your body's able to maintain the levels of bicarbonate ion and also carbonic acid, which then can react with these hydrogen ions that are floating around and maintain your pH at a certain level, no matter if you have lactic acid being released in your blood or you have excess carbon dioxide that's being dissolved into the blood. It can always react away with the conjugate base, and your blood pH remains relatively the same. And so you might be thinking, why does that matter? Well, excuse my language, but it can really do a freaking number on your body when your pH drops down too low or goes up too high. The enzymes in your body can stop working. You start to degrade different tissue types. It's really not good. Cells start to die, etc., causing you a lot of pain and eventually death. And so when your pH falls too low, in this case, your pH, say, is above 7.45, that's called alkalemia. And when your blood pH is below 7.35, you have acidemia. So your body keeps the pH, your blood buffer system keeps your pH within a very strict range of 7.35 to 7.45. And that is that for the third podcast in the series, Mcat Top 20. Hope to see you back. The next podcast is going to be on metabolism. It's going to be a two-parter, a pretty long one, another semi-important one. I think I was reading through the Kaplan books, and they have not much emphasis on this. So as I went through the practice tests and everything, I kind of noticed trends in which I was seeing a lot of the glycolysis intermediates, Krebs cycle stuff, and it ended up being a pretty important part of the test. So make sure you know that thing, and make sure you take a listen to the podcast, and make sure you put some emphasis on those topics, because obviously a lot of different places seem to think that it's not that important, but I disagree.
All right, so now for the part of the podcast called Mcat Advice of the Day. So my advice for today is that you should take as many practice tests as you can before your actual test. So I think I took 9 practice tests before I took the test. So what I did is, 9 weeks out, I started taking a practice test every Saturday from the exact time that I would be in the test to the exact time I would leave the test. So sat down in a quiet place and basically simulated test conditions, and then took that test, 9 weeks leading up to the actual MCAT. And then that way, by the time I was actually in the MCAT and sitting down and taking it, I was super used to it, and it's a very long, kind of grueling test. And so if you get used to that length, I think it's a big advantage if you can stay focused the whole time you're taking the test. And so obviously, if you practice that, you get used to it. And so yeah, that's my advice for today. Oh, and one thing that I just thought was kind of silly is, I was reading some stuff online, and people were talking about how they were simulating the test down to what they were wearing, the foods they would eat and stuff. And, they were saying, okay, well, on test day, I'm going to wear these clothes, so I'm going to wear them for this. And, I'm going to eat my sandwich with 4 carrots and 2 Triscuits, or, just something super specific. I think that shit's silly. I wouldn't do that. But obviously it is important to simulate test conditions. That way you're ready for the test when you get to it. Come on, Murph. I'm trying to podcast over here, dude.